Welcome back, everybody. Welcome back to the channel. So today we're going to be continuing where we left off. So we were kind of in the interpreter thread start function, and we talked about how to call the main method. Now I could go into, because we've already gone over this entire function, right? I could go over the main execution loop. However, I don't think that is a good idea right now because we still have one other aspect that we need to go over. Obviously, we also still have to go over the exception system, which will come later. But the other aspect that we need to go over is actually the JIT. So today we're going to be talking about how to build a just-in-time compiler. And now I'm going to start off by saying most of the code in the JIT is broken. Most of the code does not work. Now, before you click out of this video is still valid. I haven't had enough time to get around to actually building a JIT. It takes way too much time. It's going to take me months to do that. Not to mention, I'm also working on a drone project, and if I start working on the JIT, that's going to break everything, and that's just not going to happen. So in the spirit of keeping things going, I don't want to skip over the JIT, so let's just kind of jump right into it. So with the JIT, it's going to be a pretty simple system. So I don't have any pictures for today because I think it makes sense kind of how it works. So I have three levels of the JIT. Let's start at the bottom. So at the very bottom, I'm going to have the JIT layer. The JIT layer is going to be the quote-unquote high-level interface to interface with my just-in-time compiler that abstracts me away from the extraneous details of how the garbage collector or how the JIT actually works. At the level above that, I'm going to have what's called a base assembler. So it's going to be base assembler, and the base assembler is going to work basically as what it is. It's going to be the base assembler or the base class for assembling any type of data in our programming language for our JIT. This base assembler class is mainly going to be used as a way to abstract away from the actual processor that we're going to be generating the code on. Now, currently, before I actually broke my JIT and before I did like this crazy language overhaul, I was supporting 64-bit Windows operating systems. So we're going to kind of go over that today. Now, all the information in the video today is going to be applicable for you to basically build a JIT for any operating system in any processor. So even though I only have support currently for the 64-bit Windows, that does not mean you can't apply this same technique and the things we're going to be going over to other operating systems and processors. But I'm going to have what's called a X64 assembler, MBLER. Now the X64 assembler is going to represent basically the 64-bit assembler for both Windows and Linux. Now, I never really had enough time to get around to building the 64-bit assembler for Linux, but I did do it for Windows. And yeah, so that's kind of the general premise. Now, here's where it gets into the magic. Let's say I also want to write an assembler for ARM processors. So I'm going to say ARM assembler, MBLER. So basically, I would create a additional assembler class. So as you can see here, I only have the X64. I would create an additional class called ARM assembler, and that would inherit the base assembler as the base class. And then the JIT would then basically call to whichever assembler that we are running on for the specific processor and operating system based on all those various different configurations. So that's kind of at a high level how this system works, and that's the idea behind it. Now, even though this is the hierarchical nature of how this system works, I only currently have one processor, so it isn't fully in that hierarchical form, but you'll see what I mean, but that's kind of the idea behind it. So let's actually look in the file to see what we need to do. So first, you're going to want to create your JIT class. This is going to be the high-level interface, and we're going to have a couple different fields. We're going to have the thread self, which honestly, this is unnecessary. This was also predating the thread self variable that I have in my thread class, so you don't really need to add that. We also want to have a mutex, a recursive mutex. a message queue. This is how we're going to actually talk to the just-in-time compiler. And then we're going to have what's called an X64 Assembler. Now, this should actually, you know what, I'm going to rename this to Assembler. This assembler is basically going to be the abstraction level assembler based on what operating system. So currently, as I mentioned, I only support 64-bit Windows operating systems right now. But in the future, if I wanted to support other operating systems, I would say if defined, and I will put an if define here, and I would basically put a check to see, I don't know, if like, let's say for instance, OS is equal to, you know, whatever, right? Then I would basically pass the assembler that I need here. So I would have an X64 and then I'd have an ARM assembler, and I would basically split these assembler values based on what processor, using preprocessor definitions, kind of like how I have here for this function where I have these preprocessor definitions. So that's kind of the idea behind it, and that's what you want to do. You're also going to want to have an error field. This is just going to be if we have any errors with the JIT, we can just read those various errors. Now, you're going to want to create a generic constructor, and that's going to set up the assembler to null. That's going to set the error to error OK. Also, I forgot to mention, we are going to have several different errors for our just-in-time compiler. So our just-in-time compiler is obviously going to have just a generic, oops, it failed, and it's just a generic error. We're also going to have a JIT error memory. So if it tries to allocate memory for our JIT, then obviously that could potentially be an issue as well. Or we could have a JIT error max attempts. This is going to be a potential that could happen where we try to compile a function multiple times and it doesn't work. That's entirely possible. We also have error unsupported for unsupported OS or processors. We also want to have an error size, meaning that the function is too small for us to compile. And then obviously we have error OK, which just means that we're totally fine, nothing happened. So in your basic constructor, you're going to want to initialize your message queue, which is just a list of, you know, our messages. And these are going to be int32s of a bunch of functions that we're going to be calling in our just-in-time compiler. Then you want to have your basic if statement. Now here is where it gets into specifics of picking the assembler. Now, this uses preprocessor definitions, and I'm pulling this ASM JIT arch bits from the ASM JIT API. The ASM JIT API has this really nice file called build.h, and it allows you to basically, and I actually don't know where that file is. Let me scroll to the top to see. That is located, oh, it's actually here. So I basically just include the ASM JIT file, which basically inherits all of the necessary data. So as you can see here, I'm currently running on a x86 processor, but it also has support for ARM. Now, I will say that the ASM JIT API does not currently have support for ARM, but it is a work in progress. So you guys can take a look at the pull request to see, you know, how far along it is. But x86 in and of itself covers a wide range of processors and computers, so that's what we're going to be going over today. And of course, obviously, this API system does support both Windows and Linux for generating code. So if I go back to our main constructor here, this is going to be using predefined fields or preprocessor directives, meaning that this is why these values are gray, because arch bits are always going to be equal to 64. Now, you still want to have these if statements because, you know, obviously, as you compile your programming language on different operating systems, these values, arch bits, are going to change. The OS ID is also going to change. Now, the way that I set up my OS ID is I created a enum called OS, and then I check for if Win32 or POSIX, and then I set the OS ID to the specific OS that it needs to be. And I get the Win32 from here. So this is basically in the std imports, and this is how I figure out whether or not we are a Windows or Linux system that we're compiling under. So once we do all of that, so now that we've confirmed that we are 64 bits and this is a Windows operating system, I assign the assembler to the X64 Assembler. Now in the future, this is going to be OS ID is going to be equal to Windows OS, or OS ID is equal to POSIX, but right now it's just Windows, so that's why I'm only doing Windows to make sure I don't break anything in my programming language. And obviously, if none of these values are true, then we're going to just return an unsupported because that's what it is. Now let's actually go into some of the functions. So let's look at the startup. So we've already gone over the TLS setup, so we don't have to do that. So when you start up the JIT, first we're going to check to see if the JIT option is enabled. You can disable the JIT. For now, this is like a debug option. In the future, the user will not be able to do that. But obviously, if the JIT is enabled, then we want to start it up. And there are reasons for you to disable the JIT because as you're building your programming language, you're not going to want the JIT to run all the time. My JIT is extremely fast, and in fact, it's 10 times faster than the actual garbage collector can keep up. So there have been opportunities or instances where I've had seg faults happening because there were race conditions. So I turned off my JIT to basically fix those issues. So you want to create your new JIT with the constructor. Then you want to call Git Assembler. Now this is where the magic actually happens. And this is commented out for some reason. But basically, the magic happens here. So assembler, then return assembler. So basically the way it works is when we actually call Git Assembler, if you remember, we're going to initialize the assembler field only if we have the supported operating system. So when we call the Git Assembler, it's only going to return the assembler if it's not equal to null. Now, this is kind of silly, actually. I could just do that. So it returns the base assembler, and as you can see, it's not returning X64, which this field clearly is, because we want to just abstract away from the actual processor that we're running on. So when we call base assembler, if that is not equal to null, then we want to assign the error here and say if getting the assembler and then performing the initial compile is not equal to error okay, then we want to handle that. Otherwise, if everything is okay, then we start up the actual JIT. Now we've already gone over this. It just starts up a daemon thread and it creates a daemon thread called JIT, and that's it. Now, before we get into this code handling the error, we want to create a perform initial compile function. The purpose of this function is to initially compile any functions that the compiler may want to be auto JIT'd from the very get-go. This is really only going to mainly consist of the main method because obviously the way that my JIT works is we only execute that JIT function after we've returned out of scope. So if you have a giant for loop in the main method, we're never going to actually be able to run that main method at the JIT level because of those reasons. Now, theoretically, what you could do is you could just create your main JIT function. So let's say void JIT function, and you can literally pass in the PC. So you can create an int, int, or maybe a long. You can pass in the PC that you want to start with, and then in your JIT, you can jump to that address of that function to start specifically at that point. And that is something that I'm considering adding in the future, and I'll explain in this video how you can actually do that. So during the performing initial compile, you're just going to make sure that we can have the JIT enabled and either slow boot or is JIT. So meaning that the JIT flag was set by the actual compiler. Now, slow boot, what that does in my programming language is that basically forces the entire code base to be compiled by the JIT. And it's a really nice feature. And this actually speeds up the programming language a crap ton because it no longer has to try to figure out whether or not we're going to compile any of the code. It just compiles everything. And when we're compiling or as we're like going through, we're going to set the JIT to false. And then we're going to just try to JIT the function. Now, if there's an error, we're only going to try to listen for the error if it is an error compile. We're going to set the max attempts to whatever the JIT max attempts is. Currently, that is 3 for me. And then otherwise, if it's an error memory, then I return that error. Otherwise, I ignore any other errors that I get because obviously this is just the initial compile. So that's going to be it. And of course, if none of these errors get reported, then I just return error okay because I executed this function without any flaws. So if I go back, so once we perform the initial compile, obviously if there are any errors, then we want to handle them here. So we're only going to listen for the error memory error, and otherwise we'll just ignore it. And obviously, if the initial compile does not go through, we're not going to start the JIT because that's an error that I need to fix. Now, the only potential error that I could have is the JIT error memory. If you notice here, I only return the error if it is JIT error memory. If it's JIT error compile, I just set the max attempts on that actual function. So we're only going to respond if there's an error memory. If so, I print out like a helpful error message, and then I just shut down the JIT. Now what shutdown does is we just check to see if self is not equal to null, meaning that the actual JIT pointer is not equal to null. Then I check to see if we have the assembler. So if the assembler is not equal to null, I call shutdown on that assembler, I delete that value, and then I set that value to null, and that's it. And then of course I delete self, which is the current JIT instance. And that's pretty much it. So that's how we shut down the JIT. Now let's look at before we actually get into compiling a JIT function, because that's going to be the bulk of this video, let's look at actually running a JIT. So when we actually run the JIT, we're going to have all the same usual crap that we have in every single daemon thread in our programming language. We're going to check for suspend before we check for if we've been killed, and we'll respond accordingly. This allows us to work with the standard multi-threading platform, so that way it's not spinning, waiting for these daemon threads to suspend and or kill themselves. We also have a message queue check. This is just like the garbage collector, where if we have a message, we lock the mutex, and then we basically pop the function that we want to compile off the stack or off the message queue, and then we call getAssembler, and then we try to JIT that function. Now, as this JIT is running, the JIT is going to be asleep 90% of the time of execution of any single program. So the only way that we can wake up this JIT is if the message queue is not empty. So if we have a value in the message queue, then we're going to actually jump up here and compile that function. Otherwise, we're just going to sleep for 1 millisecond forever. Now, obviously, if we've been suspended or if we've been killed, so if as long as the thread is equal to running, the state of the thread, then we're going to keep spinning forever. And then after that, we'll just return out of the scope of this function. So we'll just return out of this run function. And that's it. And then when we go here, now I do have a try catch. This should never happen. I shouldn't have any exceptions, but I just do it as a formality. If we have any exceptions, I set the signal of exception to true. And when it comes time to actually exit the main thread of the JIT, I just call the standard thread self exit, and that's it. And then of course I return whatever value I need depending on the operating system. Now here's how I send messages to the JIT. I use the standard messaging system that I use for my garbage collector. You want to send a message saying that I want you to compile this function. So what we do is make sure we have both the JIT and the assembler. If so, then I guard the mutex. Again, I'm protecting the mutex here while also protecting the mutex here, so that way there's no collisions. I immediately say the function is compiling, and then I add this message to the message queue. And that's it. And I can continuously do that until basically I run out of max attempts for the actual function. So that's basically the building blocks for the high-level version of my JIT. Now we're going to step down another level. So now we're going to step into the base assembler class. So if I go in here, now we're in the base assembler class. Now let's actually see what are the various things that I do in the base assembler to actually compile my function. Now, there's a crap load of stuff in here. We're not going to go through the extraneous details of every single function, because I want you guys to not pay too much attention to the actual code that's being generated, because as I've mentioned, my programming language has changed vastly for the better, and a lot of this generated source code is wrong and it's broken. So I want you to pay mostly close attention to how I do everything and not what I'm actually doing. So in the actual JIT, you want to create a series of fields for the base assembler. You want to create a bunch of registers. These registers are going to be any register that we're going to be using by the JIT. Now, as you guys know, in every single processor, there's a thing called registers, and registers are just fast memory accessors to do basically anything you want to do on a machine. Now, before we continue on, I will say that you guys are going to need to take some classes on the x86 instruction set and the x86 family of processors. Otherwise, you won't really know what's going on and what I'm really talking about here. So just keep that in mind. Now, I also want to mention I'm not an expert in this field. So there's going to be a lot of weird stuff that you're probably going to see and notice in here. So just keep that in mind. I'm not an expert when it comes to actually generating source code. This is the lowest level I've ever been in terms of programming. So keep that in mind. You also want to create a bunch of, so you want to create the JIT runtime. This is going to be the JIT runtime used by the ASM Jit platform. This is where we can basically create all of our functions and add them to the actual runtime. After that, you also want to create a list of functions. These are going to be the list of all of the functions that we've generated in our programming language to basically be executed at the low level. And then finally, you're going to want to create what's called a memory map. Now, the ASM Jit platform allows you to create what's called a x86 memory, and this is a data structure that represents a pointer to a value in memory. So as you can see here, I have various different data structures. A perfect example is data structures for accessing the thread object, the stack element object, the frame, the method, the sharp object. These are all objects that you're familiar with if you've been following the series. For example, the thread object, if I go here and I go to thread.h, that represents this class. So this allows for me to create a memory map of this class. So for instance, if I wanted to access the calls field, I can do that. Now, one thing that I want to mention is the way that ASM Jit works. It does not force you to basically utilize the entire memory map, meaning that even though this thread object, I have no idea how many fields it has, maybe it has like almost 20. As you notice, I only have 13 fields here. That is not the total amount of fields that this class actually has available. So I'm only accessing the fields specifically that I need to access. So just keep that in mind if you're wondering why I'm not having the full values of each data structure. So when it comes to building your JIT, you're going to have a few basic preliminary functions. Obviously, you're going to have the constructor, which sets up the runtime and then initializes the functions that we have down here. And that's pretty much it. And then you're going to have a perform initial compile. We've already gone over that. You're also going to want to have an initialize function. This is going to be a function where we initialize our assembler. And in this initializer, I'm not going to go through every single function because every single function is pretty much the same. But first, you're going to want to call initialize registers. Now, the way that I have this working, where I have basically this hierarchical structure, is I have a bunch of virtual functions that represents a way for us to abstract away the source code for the specific processor. So obviously, depending on the operating system as well as the processor, you're going to have different types of registers. So I created this initialize registers function, which the x86 assembler then has here, and this has the function implemented where it overrides that virtual function from the base assembler and it initializes those registers. Now, as you can see here, when I create the x86 assembler, I build the base assembler, which calls this constructor, and then I call into the initialize function, which is by the base assembler. And that function then calls upwards back to the same object, initialize registers, which then is going to call this initialize registers function that is in the x64 assembler class. So that's kind of how it's going to work throughout the entire assembler. Now, as you can see here, I only have 4 functions, or was this 5 functions? Because I'm only supporting one processor, I do not have the full list of functions here for delegating work to the specific processor. Ideally, what you want to do is you want to have a function for every single opcode in your entire programming language, as well as various different sections of the JIT function, because that's how it's going to kind of work in general. But again, I only support one, so I don't have everything set up yet. Now for initialize registers here, I basically have all the specific registers that I'm using for the Windows 64-bit operating system. Now I'm not going to go through every single register and why I have it. If you guys are curious about my JIT, it is heavily commented all over the place. I mean, I have comments almost every couple of lines, so you can basically get a general idea of what I'm actually doing in the JIT without really having to know specifically what each of these things are, what they mean. Like, it'll explain it to the right side. So I'd recommend you going to the JIT folder and the runtime and just looking through all this code. It's littered with comments. So I think that'll definitely help with you guys actually building your JIT. So once we actually initialize our JIT, if I go back to the base assembler, now it's time to actually compile the code. Now, the only other function that we really have is this try_jit function. And this try_jit function is responsible for calling all of these other functions in our JIT. Now, it's a lot of functions, and I'm not going to go through all of them because this video would be entirely too long. We're just going to go over the high level of what I'm actually doing. So when I try to JIT a function, I'm going to set the default error value to JIT error OK. And depending on certain values, depend on the result that I get. So obviously, if the function is not JIT'd and the JIT attempts is less than the max attempts, I try to compile it. Otherwise, I do a check to see if the JIT max attempts are greater than max attempts, and if so, then I return that appropriate error. Now, when it comes time to compile, I assign the error field to the return value of the compile function. And if that's not a perfect compile, then I just increase the amount of attempts that I did on that function. So that's how I end up going over the max attempts. Now, when it comes to actually compiling the function, this is a humongous function. Now, before we get into this source code, I'm actually going to write out how this function looks if we were to write this in C++, and then we'll get into the actual details of each section of code. So the way that it works is every single JIT function returns a void value. The reason is because I have a imaginary stack, so I'm not going to be returning physical data from that function. I'm going to be putting that data on the imaginary stack and then processing it that way. So let's call this JIT function underscore function, and the JIT function is going to take in a Jit context. So it's going to take in a Jit context, which is right here, and I'm going to call this JCTX. The Jit context is going to be the base context information for the actual JIT function. So basically, this is a fire and forget context. So we're going to use this context one time. As soon as we get into this function, we're going to basically inspect all this data and immediately save it into registers. Now, let's see. So when I immediately jump into the function, I'm going to have a check. So it looks like this one here. I'll do this. So I'm going to check the Jit context and see if the Jit context and the function inside of there, what is it called? It is called the caller. So as you can see, things have changed. So if I check the caller, I'm going to check the JIT labels and check to see if it's equal to 0. If so, then I'm going to go to label. So LBL, we'll get into what that is in a second. But basically, we're going to want to create this JIT labels field inside of the methods. Why is it not working? Why is this? Okay, I'll have to check that later. Basically, we're going to have the JIT labels field here, and that's going to be basically the way for us to bounce around in the code. Because you need to realize something. We're compiling this code down to direct machine code. So it's not going to be the same as if we were executing in the main loop of the thread. We don't have the same luxuries that we're afforded when we're actually executing the instructions at the high level. For instance, if I execute this no-op instruction, I just call branch, which literally calls branch no increment, which dispatches to the next instruction. And the dispatch just goes to the next instruction in the go-to table. And this opcode table has the actual physical address in memory of where the location of the start of the next instruction is based on whatever the opcode is in that actual opcode table. So we're doing something very similar here. So at the initial starting point, if the first element address value is 0, then obviously that's bad because we're going to have this if statement as the first part in our function. So we can guarantee that the label, even if we have an instruction of no op, right, immediately after this if statement, then we can guarantee that the value is not going to be 0 because we have this as the initial starting code. So that's how I verify that. Now what I do is I basically create a labels array. So in here I have various different fields. So I'm not going to go into all of them. I have a bunch of local fields in here, but I do have one called labels. So it's a int 32 underscore t and pointer labels. So I have an int32 of labels, and I'm going to allocate this on the actual stack. So I'm going to say new int 32 underscore t, and it's going to be based on however many instructions that I have. So let's say, I have 10 instructions. Then basically what I'm going to do is I'm going to say labels at 0 is equal to the address of the first instruction. So let's say the first instruction is no op, right? And then we do whatever we need to do for that instruction. And then let's say after that, I have a interrupt instruction. And if I move this back, and let's say I do whatever I need to do for that instruction, each instruction is going to have its own address value of where it starts in the function code. So I'm basically going to assign the address of the no op instruction, and then I'm going to assign the address at 1 of the int instruction, and so on and so forth, right? So I'm just going to go down the list of label and assign all these addresses as values in the actual function. Now, we're also going to have a bunch of other things. So I have a different way of how I do thread stack checks. So as we're executing each instruction, we're not going to be doing, in order to basically speed up the programming language, we're not going to be checking the state of the thread every single instruction. If you guys remember, as we're executing instructions, we have this brh command, and this brh define statement does a brh no increment, which checks to see if we have a signal. And this has signal check basically checks to see if we've suspended, if we've killed ourselves, or if we have an exception to catch. Now, this is time consuming. This is unnecessary code, and we're not going to, these events are not always going to happen every single second, right? And based on how my system works, I basically only do this check when I call a branching instruction. And a branching instruction is defined by, if I scroll down here, jump not equal to, go to, brh, if equal to, and if not equal to. So you don't need to know, I did a video on explaining what my instructions are and what they do, but basically any instruction where you're going to branch to a different piece of code, you're actually going to want to do the check there, because these things don't happen that often, and that allows us to make sure that the thread is still okay and we don't have any issues. And this actually works perfectly. Now, I also do this thread status check in other spots as well, but the main point is that you want to do it after a qualifying event. I also call thread status check immediately after I've created a new array, right? So obviously when I create a new object, I could potentially have an exception thrown for an out of memory. I also do when I cast objects as well as call functions. So I do it in other spots. However, again, the point is that you want to do it in a qualifying event. You don't want to just constantly check the stack if you're going to call like no op, for example. There's no point in doing that. So there's that. And so now we're going to also have another section. So we're going to now have the thread stack section. So I'm going to create a thread underscore stack section here, and that's going to allow us to basically check the stack. So I'm going to be lazy and just go here. I'm going to copy this and go back to the base assembler, and I'm just going to paste this here. So this is basically what I do. So in the thread stack section, I do that. So let's say I have, a qualifying instruction. So let's say I call a function, right? I'm going to write the code in there to call the function, and I'm immediately going to jump to the thread stack section. Now, there is something you guys are going to need to know. I cannot just jump here to the thread stack section because it's going to be at the bottom of the actual function. So what I'm going to do instead is actually put in the PC of where I need to go back to into a specific register, and then at the very end, I'm going to say go to, and then I'm going to jump to the actual address in the labels table. So I'm going to go to labels, and then let's say I use the, I don't know, EBX register in the actual CPU. I'm going to go to labels at EBX, and that way I can bounce back up to the top. So let's say after the call function, I have another no op instruction, let's just say, because I'm bad at giving examples. If I want to jump to the next instruction after I do a thread stack check, I'm gonna call the function, go to thread stack check, and before I do that though, I'm gonna say the EBX register is equal to, this is the third PC, so I'm going to say PC plus 1. So that's basically going to be the next instruction. So I'm going to say EBX is equal to 4, because, or actually 3, because it's 0 based. So instruction 0, 1, 2, 3. So basically after I check this stack, I'm going to say after you're done, jump to no op, because that's the next instruction that we need to execute. So once we do that, then we're good to go. And then we basically have a way to do that. And then we're going to basically execute all of these instructions in the actual function. So I'm going to scroll down, as you can see here. So here's the start of the actual address. And here is what's important. So again, you don't need to know all of the details of how the JIT works. And as I've said before, there's tons of comments, so you guys can easily look in here. There's comments on almost every couple of lines of code explaining what's going on. As we're executing this, we're going to be binding the label at the labels field that I was talking about up here. We're going to be binding each label to each instruction that we're compiling as we're building the physical source code. So that way, when we actually jump to that array, we can do it appropriately. So then after that, let's scroll all the way to the bottom. So as you can see, I'm generating a crap ton of code. Another thing that I will mention before we continue on is you can do what's called instruction stacking. And this is going to be a new concept that I'm actually going to be implementing in my JIT, but this is a tip for you guys in the future. As you're building your JIT, you're going to have specific instructions that are going to be generated for every single opcode in your garbage collector, or in, why do I keep saying that, in your virtual machine. And here you clearly know what instructions are being generated. And because of that, you have an advantage. You know that if certain things are going to happen here, and if you're executing another instruction that does something similar to the previous instruction that you just generated, you can actually switch things around to accommodate that next instruction, so that way you're not repeating unnecessary code. So just keep that in mind as you're kind of like generating things. You can do some instruction swapping and really cool stuff that makes it a lot faster. Now, another thing that I just remembered, sorry if I'm bouncing around too, by the way. How did I generate all these instructions? Obviously, I'm not a genius. I don't know half the time what the hell I'm doing. I just wing most of this stuff. So the way that I actually figured out what instructions I need to build for each of these opcodes is I literally used a tool called Godbolt. Guys, you need to use this tool. I implore you to use this because it's going to save you a lot of time and headache. Now, obviously, I still did take some classes on the x86 processors to kind of still get a basic understanding of what's going on. But as you can see, Godbolt is a lifesaver because literally you can just write in C++ code and do whatever you want. So let's say I create a data structure of foo, and let's say foo has in it an integer of I, right? And let's say I want to access that integer. I can create a foo field, call it f, and then say f.I is equal to 10, and be done. And literally what I ended up doing was transposing my entire source code of my virtual machine into this thing here. And I mean, you can like add files and stuff and do all types of stuff and compile all this source code and literally just inspect what is generated. And you can change the options here. You can, this is a standard GCC compiler. So you can say -M32, which forces the compiler to compile for 32-bit operating systems. You can also do -03 or any other standard options that come with, compiling C++ code. And you can like fully optimize, like 03 is the maximum optimization limit. And you can see what's generated as well. So you can literally just go to town and just write all of your source code in here and just copy and paste it. That's literally it. The actual assembler that I'm using, done by the ASM Jit, has a bunch of really nice functions. So like if I do this, I'm going to say a assembler dot and then move, MOV, and then do this and do a control P, and you can literally see the move instruction takes X amount of parameters. So you call a function and you can literally use this with Godbolt and use code completion as well to basically make sure you don't screw up generation of your actual source code. And it's pretty nice. So I definitely recommend checking out Godbolt. This has saved me a crap ton of time and just like generating all my source code. So once you get down to the actual end of the function, so actually, do I have to keep going? Okay, so we're at the bottom. Now I'm going to skip over the few sections here. So this is kind of the end of the section. So this is the label section I was talking about. This is actually generating the code to update that labels variable that I was talking about to assign those values to that array and be able to do all that good stuff. And then I also have my thread stack check section immediately below that. So there's that. And then finally, I have what's called a constants section. So I'm going to scroll all the way back up to the top. My constants section is going to consist of constants, any constants that I have inside of here that I need to use. So as you guys know, you can't just hold double values, obviously. So if I don't know, want to assign the value 0.12345, then I'm going to need to put this as a constant at the bottom of the function in the constant section, and then reference that constant value as a value. So if I want to, I don't know, set register in my actual virtual machine, set the EDF register, which is a virtual machine register in my fictional programming language. And I want to set that value to the 0.123 blah, blah, blah. I can say that is equal to constants at index of 0. And that then basically accesses the pointer of constants and gets that constant value from there. So that's going to be it for today, guys. That's pretty much it. Now, I know I didn't really go too much into the code. I did go a little bit fast, but I hope you guys did appreciate this more high-level approach to how my JIT system actually works. And hopefully it helps you kind of understand the code as you're kind of looking through it to see, what's going on. And again, most of this code is broken. As you can see, there's a crap ton of red errors here that I still have to fix. I just don't have the time to do it. But once you kind of get done, so once you're at the very bottom, you're going to want to add the function to the JIT runtime. Now, you're not guaranteed for adding this function to actually work, because if you make a mistake in the API and pass the incorrect data or an uninitialized data structure to one of these functions, the nice thing is that you will actually get a runtime error. So if you generate an instruction incorrectly, you'll actually get errors at the runtime, which is really nice. So basically, we just want to make sure that everything goes well. And if we have an error, we say JIT code error of whatever. And there's various different errors here. So, I mean, the JIT runtime has all different types of errors that kind of protect you from hurting yourself when you're actually generating source code. So that's really cool. And otherwise, if we don't have an error, obviously you want to put the error compile if you do have an error. But then we just set up the function. So we say the function has been, in fact, JIT'd. We set the JIT call function, which if I go to the method, that is going to represent this here. So you actually want to just set the JIT function, which is going to be a reference to the function pointer in physical memory that is going to be created. So the way that the JIT runtime works is that all these functions that we're going to be generating are going to be compiled and saved in memory as we're executing our programming language. So we're going to have to access that specific pointer to actually call the function. And then we basically push back that function on the functions list, and that's it. Now, obviously, if we did not get into this if statement, we are going to return the appropriate return value. So if we did the check where it's too small, then we're going to say JIT error size. Otherwise, we just say we couldn't compile it. And that's it. So that's pretty much everything. And here are the if statements that I was just talking about to return those specific errors. Now, as we're executing code in here, we are going to be calling various different functions at the bottom. So I have what's called helper functions, and you're going to want to create these because they basically allow you to generate a bunch of code and not have to actually continuously write that code. So I basically just pass in a bunch of parameters. And for instance, if I want to do the stack check for whatever, right? Like if I go back to the opcode and I go to has signal, I also do a stack check as well. So where's that at? So if I go to the thread, if I do a search for stack underscore check, you can see here that I'm doing this before I call the rstore function. So if I want to generate that same source code, The stack check just makes sure that, we haven't overflowed and it throws an exception. Then I have this helper function that generates all that source code for me. So that's just another way that you guys can do that. And that's pretty much it. Hope you guys enjoyed the video. As usual, if you have any questions, as always, put them in the comment section below. And of course, if you guys would love to help support the channel, you can always head over to the GitHub repository at androidfcd/sharp. And when you do, definitely watch Star and Fork, this repository. That gives this language a lot more visibility and let other developers know this language exists. Also, if you're curious about some of the various things that I'm looking to add in the future, or some of the stuff that I've recently done, you can always head over to the roadmap section, and in there I write some pretty decent descriptions of various things that I'm looking to add in the language, as well as it's a very nice view, so you can kind of see in real time what I'm up to with the development of the actual programming language. So that's going to be it for today. As usual, if you're new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.